Hello dear students, welcome to the lecture series on microelectronics. This is lecture number 9, frequency response of MOSFET. Now in the previous lecture, we tried to cover up MOS internal capacitances, wherein we saw how MOS internal capacitance will impact the amplifier's overall gain functioning. Now in this lecture, we are going to see how does the response for a particular frequency for a MOSFET amplifier will be seen in this particular lecture. Now I am going to refer these particular sections of Sedran Smith's 5th edition. So please refer these sections for further readings. Now this slide shows typical frequency response of an amplifier. Now as you can see, the entire amplifier's gain response can be broken into 3 different bands. The first band till a frequency FL is known as lower frequency band, and from the frequency FL till FH it is known as mid band, and after FH that particular frequency band is known as high frequency band. Now as you can see, the gain versus frequency over a log graph is shown over here, which is marked over here. Now you can clearly see between a frequency range FL and FH where the gain is very linear or constant, that particular band is known as mid band. Now there is a sudden fall of gain before FL and after FH. So gain falls off due to the effects of coupling and bypass capacitors over here, and gain falls off due to internal capacitive effects of MOSFET, or it could be even the same case is acceptable when it comes to BJT also. Now how I am going to say, or how did I say that this reduction in the gain in the higher frequency band is particularly because of internal capacitive effects, and the gain is reducing here, and I am saying that the gain is reducing because of coupling and bypass capacitors. How I am going to say that is we are going to see in the subsequent slides. Now few observations when I say a term frequency response. Now basically analytical solution of amplifiers in frequency domain is very complicated, and hence we need to be considering all the parameters with utmost care. Now response, that is gain of an ideal linear amplifier, should be independent of frequency. So that's what we usually say. Otherwise the signal shape would be distorted by the amplifier. So when we say this particular sentence, a practical amplifier acts as a linear amplifier only for a range of frequency called as midband. As you can see over here, practically speaking, an amplifier's gain will be constant within a band of frequency. That's what we call it the bandwidth or a midband of the particular amplifier. Lower and upper cutoff frequencies identify frequency range over which amplifier acts linearly. So again, after FL and before FH, whatever is the range of frequency, so that will be my range of frequency where my amplifier will be having a constant gain. Now here I have said why in the high frequency band the gain is rolling off, or I have mentioned a statement, I have made a statement wherein I say that because of internal capacitive effects the gain is rolling down to 0. Now here I will make one more statement where I say amplifier response at high frequencies, that is near upper cutoff frequency, is very important for stability considerations. Now again I will try to give throw more light on this particular statement in the subsequent slides. Thus we are mainly interested in midband properties where capacitors can be ignored and poles and zeros of the amplifier response, that is the impact of capacitors, can be reduced or it can be ignored to 0, which means this is the band where if I operate, then I can say that there will be no impact of capacitance and I can ignore all the effect of capacitance. But if I am operating over here and here in this region, then definitely I need to be considering my impact of all the capacitances that are implicitly present in the MOSFET and that are explicitly attached in the circuit. Now when I make a statement, what do we mean by capacitors can be ignored? what is exactly it means. Now, to get an insight of this particular aspect, a small explanation with respect to how capacitors impact the frequency, how capacitor and frequency are interlinked. Now, basically, when I say impedance or capacitive impedance, that is represented as Z, it is given by the term Z is equal to 1 over j omega c. Now, omega represents 2 pi fc. Basically, it is nothing but my frequency, capacitance, and this is my impedance. So, basically, in a simple terms, I can also say that the resistance offered by the capacitor, I can call it as a capacitive impedance. Now, let's try to analyze, or let's try to make this analysis very simple as possible by ensuring two particular values. Now, at very high frequencies, now when I say at very high frequency, let's say this f or omega value, if it is very large or infinite, ideally speaking, so 1 over infinite will be what? 0. So, my capacitive impedance will be tending to 0, which means I can make a statement at very high frequency, my capacitive impedance will tend to 0. If it tends to 0, what does that mean? Which means there will be no resistance offered by my capacitor. That means my capacitor is going to behave as a short circuit. So, please do remember this particular statement. At high frequency, capacitors acts as a short circuit. The same is the case in the other way. At low frequency, that is when I put omega or f equal to 0 over here, 1 over 0 is infinite, Z is infinite, which means it is offering a huge resistance. The capacitor is offering a huge resistance, that is capacitive impedance is very large. If that is the case, then nothing can pass through that particular capacitor, and hence capacitor acts as an open circuit. So, please do remember these two statements, that we are going to make use of these two particular statements repeatedly in almost all the analysis whenever the term frequency comes into picture. Now, for the above two limits, the circuit becomes a resistive circuit. That's what I was telling, and we do not need to solve the circuit in the frequency domain. So, whenever I apply these two conditions, suddenly my capacitor behaves either as an open circuit, which is offering a huge resistance, or it is behaving as a short circuit, which means it is offering no resistance. So, under these two scenarios, my capacitor will be behaving as a resistive circuit. Now, when I say ignoring capacitor, it only means that we operate either at high enough or at low enough frequency such that capacitors becomes either open or short circuits, leading to a resistive circuit. When I say capacitors can be ignored, which means I am operating either at very high frequency or either at very low frequency. So, hence the circuit is modified by the presence of the capacitor. So, elements will be shorted out or elements will be opened up. So, this is what the analogy when I say capacitors can be ignored. So, please do remember these two particular aspects. Now, again, I use the term high and low. I say high and low frequency. When I say high and low frequency, these high and low frequency comparable to what? So, what is the reference point? So, for that, let's take a small analogy of this particular MOSFET. This is a small portion of your common source amplifier, which is having a source resistance over here, and I am attaching a source capacitance at the source lead between source and ground. So this particular node has got certain impedance, and that is given by Z equal to R parallel 1 over omega c. So this is the overall impedance offered by this particular resistive network or this particular impedance network. So let's try to figure out how my capacitor is going to impact the operation of this particular circuit here in this portion at two different frequencies, one at low frequency, another at high frequency. Let's see. Now, capacitor approximates an open circuit at low frequency. That's what the statement we made. So when we made a statement over here, so basically at low frequency the capacitor is behaving as an open circuit. So let's say I am considering a low frequency. So let's take a simple example with few different values and try to substitute and then figure out what will be the impact of frequency, or basically when I say low frequency and high frequency, what will be that particular threshold or limit. See, when I say low frequency operation, high frequency operation, low frequency with respect to what, I need to mention that. So to mention out that, I need to figure out what will be my f value. So in order to figure out that, let's take a small example wherein I am considering R is much smaller than 1 over omega c. So why I am considering this? So basically when f is low, because now I am taking the condition of low frequency, here omega indicates 2 pi f, and f is very low, 1 over low value will be high and R parallel a high value. So basically now here if I consider R as 1k and f value as 10 hertz and c value as 10 microfarad, and if I do calculate, so here f into c, see this omega will be having a value of 2 pi f and c. So 10 hertz into 10 microfarad will fetch me a value of 1 microfarad. 1 over 1 microfarad, I'll try to ignore this particular term. 1 over 1 microfarad will give me a value of 1 mega. So 1 kilo parallel 1 mega will definitely fetch me a parallel combination resistance of nearly 1 kilo ohm. So basically small resistance parallel a large resistance will always get a small resistance. So now what is the case over here? This particular term has resulted into 1 mega and this is 1k. So almost I'm going to get an impedance of 1k. So what is the combination? So this is larger than this. So basically that's the reason I have taken over here. R is much less than the combination of this. Under this scenario, what has happened to my impedance? Z has the value of Z has reached a value of almost 1 kilo ohm, which is the value of R. Hence my impedance will be almost equal to R. So this is what I'm going to get when I operate this circuit at a low frequency. Let me repeat it once again. At low frequency I am considering C value as 10 microfarad, F as 10 hertz. The combination of that will be equal to 1 microfarad. 1 over 1 micro will be 1 mega. 1 mega parallel 1 kilo will be almost equal to 1 kilo. So Z value will be equal to 1 kilo, which is nothing but my R. So hence my impedance is reaching a value of R when under this condition, under low frequency. And under low frequency, the combination of R and 1 by omega c, among these two, 1 by omega c will be much larger than R. Hence I have taken this particular term. So that's the resultant I am going to get the impedance equal to R at low frequencies. So if I just readjust these terms, R much less than 1 over omega c, which means I can also write omega much less than 1 over RC. So which means when I say a low frequency, just now remember that low frequency indicates that frequency has to be much smaller than the combination of 1 over RC, which is almost equal to the low pass filter's cutoff frequency. The same case is applicable when I talk about high frequency. Again, let me take an example of this. I have taken over here. When at high frequency, my F will be very large. So I have taken 1 megahertz. C value I kept it as 10 microfarad only. R I have kept it as 1 kilo only. Now F into C. So now the value is 1 mega into 10 micro. So 1 mega into 10 micro will fetch me a value of mega, and micro will cancel out. That again I'll get a value of 10. So 1 over 10 will be 0.1. Now R is 1k. 1k parallel 0.1 will be equal to what? Almost my impedance, because 1k is large value, 0.1 is small value, and if I do the parallel combination, I'm almost going to get a value of 0.1, which is negligibly equal to 0, which means my impedance is tending towards 0. So that's what I have obtained over here. So basically here I am going to get 1k parallel 0.1, I am going to get the impedance value almost equal to 0.1, which is nothing but the value of 1 over omega c. So under this scenario, my impedance is almost equal to 1 over omega c. That's what I have written over here, which is nothing but it is tending almost to 0. And in this scenario, what is the value of 1 over omega c? It is very low compared to R. Hence, I have taken this condition. Now, slight adjustment. I bring omega over here and bring R over here. So now omega should be much greater than 1 by RC. So that will tell me the particular condition with respect to high frequency. So when I say high frequency, my frequency should be much larger than 1 by RC. When I say low frequency, my frequency must be much smaller than 1 by RC. Now these are the two cases that define the low frequency and high frequency. Now when both R and 1 by omega c are equal, then definitely we don't have any problem. Under that scenario, I say that omega, or the frequency of operation, should be almost equal to 1 by RC. So this defines the reference frequency for both low and high frequency of operations. Now, finding frequency response of amplifier. Now basically we now figured out that there are 3 bands of capacitors: the lower frequency band, higher frequency band, and the mid band. Now basically we'll try to identify low frequency and high frequency capacitors by using absolute limits, wherein we try to say, instead of saying f is very less, I say f is equal to 0, and instead of saying f is equal to very large, I say f is equal to infinite. By putting these two assumptions, I'm going to try to get which frequency or which capacitor is going to impact which frequency. Now for biasing, now please do remember, this is one of the concept which is repeatedly asked in many of the competitive exams. For biasing, what would be the values of capacitances when you deal with the frequency response of amplifiers? Now do remember, when you do biasing, what sort of voltage you are applying? We will be applying DC voltage, and when we apply DC voltage, what will be the value of f? F will be equal to 0, because frequency will be constant, it will be 0. So under that scenario, when I say f is equal to 0, what will be the status of capacitance? When f is equal to 0, all caps will be acting as an open circuit, or basically behaving as like an open circuit caps. So when I use any biasing technique, my capacitors will be acting as an open circuit. So basically we'll try to figure out the low frequency capacitor, high frequency capacitor, and the resulting resistive circuit, which gives the midband properties. So which is what I mentioned over here, this one and this one, and based on those values we'll try to obtain the resulting frequency response. So there is one method known as time constant method to find the value of FL and FH. So we'll try to discuss that in depth by taking an example, numerical example. So let's not try to worry about that. So moving ahead, so this is what I have summarized the impact of various capacitors depending on the frequency of interest. So like I told, this is the lower frequency band, this is the higher frequency band, and this is the mid band. Now when f is tending towards 0, that is at lower frequency, all capacitors are acting as an open circuit, and this limit is used to find low frequency capacitors. And when f is tending towards very large value, that is f is tending towards infinity, all capacitors are behaving like a short, and this limit is used to find the high frequency caps. So to summarize, to compute FL, I make high frequency capacitors open, I'll make these high capacitors open, and I include low frequency capacitors. If I do this, then I can compute FL. And to compute FH, I include high frequency capacitors and I short the low frequency capacitors, because basically low frequency capacitors can be shorted, it cannot be open. When I want to calculate the midband frequencies, I use both the conditions that are prevailing in FL and FH, that is, I open up the high frequency capacitors and I short the low frequency capacitors. Thereby I am going to get the midband frequencies. Now just remember these concepts as of now. In the subsequent slide we are going to get, or in the subsequent lecture we are going to solve a numerical where everything will be made crystal clear on how these things work. Now coming to the point, remember in the very first slide I mentioned, I can just go, gain falls off due to internal capacitance. Now I told, how did I mention this is happening because of internal capacitance only, and how is that these gain is falling off below FL because of coupling and bypass capacitance only? How is that? How is that I'm going to identify? How to identify that? How to find which capacitor contribute to lower cutoff frequency and how to find which capacitor contribute to upper cutoff frequency? That's a simple technique. So let's consider this circuit. Whatever the analysis I am doing with respect to simple common source amplifier, considering a common source amplifier. So this is a simple common source amplifier circuit I have. Now I am dealing with which all capacitors contribute to lower cutoff frequency, which means I am dealing with an absolute zero value, absolute end, that is f is equal to 0. So again I request everyone to remember, when f is equal to 0, capacitor is behaving as an open circuit. When f is 0, if V0 does not change, which means that particular capacitor does not contribute to FL. Another way, that is the higher frequency capacitor. Or by making f equal to 0, if V0 tends to 0 or it is reduced substantially, when I say V0, it could be either gain also, because usually when I say V0 by Vi will be nothing but your gain. So gain and V0 are almost interlinked. So when V0 is reducing substantially or it is tending towards 0, by making f equal to 0 in that particular impedance where that particular capacitor is present, then that capacitor contributes to lower frequency, or basically that is your lower f frequency. Let's try to figure out here. As you can see, now there are two capacitors. One is CC1, a simple example, and then is CL. Now let's try to make CC1 open. Why I am opening up? Because under low frequency, as I told, the capacitor is behaving as an open circuit. So if I open it up and if I open it up, what is the condition? If I open it up, if V0 does not change, then it doesn't contribute. If V0 changes in the sense it has to reduce substantially, then it contributes. So what will happen if I make it as an open circuit? If I make it an open circuit, then no signal will reach the amplifier circuit or MOSFET, which means I am not going to get any output. My output will be tending to 0. Which means by making this an open circuit, my output is drastically getting affected, which means CC1 contributes to lower frequency, which means the coupling capacitance is a lower cutoff frequency capacitor, or because of the CC1 only, I can alter the value of FL. Again the same case over here. If I make it an open circuit, see, at a time I can do only one capacitor analysis. When I am doing with respect to CC1, need not to touch CL. When I am doing an analysis with respect to CL, need not to touch CC1. So when I am open circuiting this, let's keep it as it is. Now all the input is coming and everything is operating, and I am getting the output over here. Even if I make it an open circuit, that is not going to hamper my output, which means making an open circuit for CL doesn't hamper or doesn't have any reduction in my output voltage. That means CL does not contribute to FL. So this is how simple analysis that I can do, and maybe you can use this same technique for solving any sort of problem. The same thing can be done with respect to upper cutoff frequency. Now again the same rule, when V0 does not change, then that capacitor does not contribute, and if V0 reduced to 0, then that particular capacitor contributes. Now when I am dealing with respect to upper cutoff frequency, which means I am using an upper limit wherein I say that f is tending towards infinity, which means when f is tending towards infinity, capacitor is behaving as a short circuit. So I need to be shorting individual capacitors for my analysis. Again, let's take the same circuit. This is the same circuit, the same master circuit, CC1 and CL. So let's short CC1 first. If I short CC1, will my output reduce? Never, because whatever my input is there, that is going to pass, and I am going to get the output as it is. So which means shorting CC1 doesn't have any impact on output, which means CC1 is not an upper cutoff frequency. And that is true also because already we have figured out that CC1 is contributing towards FL. If CC1 is contributing towards FL, definitely the same CC1 cannot contributing towards your FH. Now what is happening with respect to CL? I am shorting over here. Now if I short and if I put the input signal over here, all the operation happens, and the moment output is coming, output is getting drowned, or basically my output is, or I can see the output is connected to ground, which means my output is tending towards 0 if I short this CL, which means CL is contributing towards whatever the high frequency component is there. For that, the high frequency component is directly related to the CL term. So this is how I can figure out which all capacitor will impact which frequency, upper cutoff frequency and lower cutoff frequency, and based on that I can tackle those capacitors and improvise upon that, so that I can increase or decrease this FL. Remember, more the mid-band range, the bandwidth, more bandwidth, the better will be the amplifier, which means more the bandwidth, the amplifier will be acting as a linear amplifier, which will be giving you a linear output. Linear output doesn't mean a straight output. Linear output in the sense it will be giving constant amplified output like this. There will be no distortion. That is possible only when this band is very, very large. And how do you make this band large? You push this here and you push this FH towards extreme right, and in order to push that, you need to be knowing which are the capacitor that contributes to FL and which are the capacitor that contribute to FH. If you know that, you can play with those capacitors and you can alter the midband gain. But there is one more difficulty in doing this. If you stretch this FL towards 0 and if you stretch FH towards more and more towards the right end, what is happening, though the band is getting straightened up, but the gain is drastically getting reduced by almost 3 dB every time you stretch it for a particular decade. So there is again a trade-off between the continuous midband and the gain. So that is what we call it as a gain bandwidth product. If you want to have a more gain, then this band has to be as small as possible. So this is how one can say. Now the lower cutoff and higher cutoffs are reduced, the bandwidth is also reduced, but the gain has increased. If I want to, so if I do this way, I have increased the bandwidth. I have made FH and FL and FH move this way, but what is happening over here? So if I increase this like this, the gain is getting reduced drastically. Again, we'll throw more light on this when we deal with respect to feedback amplifiers down the line in the subsequent lectures. But as of now, you remember the gain bandwidth product is always a trade-off when we design any amplifier circuit. So this is how we figure out the upper and lower cutoff frequency. So that's what is the summary over here, computing FL, midband and FH. So I can, whenever I talk about the higher frequency, you just short the capacitor. Whenever I talk about the lower frequency, you open up the capacitor, and depending on that, you figure out output voltage. If it changes, it is impacting. If it doesn't change, that particular capacitor is not impacting. So thereby you construct the different circuits incorporating the impact of different capacitive impedance and the frequency. So this is a simple plot diagram of how the low frequency response of an amplifier looks. So basically I have made it a very generic thing over here. I have mentioned here the gain of the amplifier V0 by V sig mentioned as AM multiplied by different poles. Now here, what does the pole, how do I signify the pole? The pole location or the pole value signifies the value of different capacitive impedance. So here I had CC1 CL, so which means I am having two poles. If I consider one more capacitance, I need to be considering one more pole. So based on that, I will getting more and more poles over here. So whichever value among all the threes, whichever impact is large, that capacitor will be having a main or large impact on the gain of the amplifier. So this is how a general thing I try to give for the low frequency response, wherein compute the different value of capacitance and arrange it in the form of transfer function. Whichever capacitor whichever capacitors, or because of which capacitance the frequencies or the gain is getting impacted largely, that particular capacitor will be playing a vital role in the determination of the gain. Now the same thing we have done it a little bit in detail considering a common source amplifier. Again, whatever the analysis I am doing, I will be doing with respect to common source amplifier. So I have CC1 being open, CC2 is being open, CS is open. So when I do all these things, whenever I give the input, if output is getting to 0, then it is going to have an impact. If output is not getting changed to 0, it is not going to have an impact. It is not going to have any impact. So that's what we try to analyze over here in these cases. The same thing I apply to this entire circuit, and based on that, since there are three capacitors, there will be three poles. So each pole location, the omega P1, omega P2, omega P3, I'll have these particular values. Now in-depth calculation, you can just refer Seta and Smith 5th edition for detailed calculation I have mentioned over here. And when I get the three poles, so which pole has highest impact? Let's see, if I consider omega P2, this pole, if it is giving you maximum impact, which means the capacitor CS is playing a major role in overall determination of the gain. If by chance omega P3 value is large, that means CC2 will be having that particular impact on the frequency, which means CC2 is the strongest capacitor in the entire circuit. The same is case with the CC1. If omega P1 value is large, then CC1 will be playing a major role in the determination of the frequency. So this is how we can summarize. So we did the frequency response of the common source amplifier, where we analyzed how to determine the various aspects with respect to gain, with respect to lower and upper cutoff frequencies. We figured out low frequency response. We did all sorts of those things. So these are the possible semester end questions. Please go through it. Thank you.